Today we are going to learn how to implement a random forest classifier from scratch. We will go through every step in detail, making sure that even if you have no prior experience, you will be able to follow along and understand how everything works. We will start with the foundational concepts and gradually build up to the full implementation. Let me briefly summarize what we are going to do. Random forest is a machine learning model that combines multiple decision trees to make predictions. Each tree is trained on slightly different data and features, and the final result is determined by majority voting. First, we create a decision tree class to define an individual decision tree. This class is responsible for building, training, and making predictions using a decision tree. Since decision trees split data to learn patterns, we first define an entropy function to measure the impurity or randomness of a dataset. Lower entropy means the data is more pure, while higher entropy means the data is more mixed. To determine the best place to split the data, we implement the information gain function. It calculates how much uncertainty is reduced after a split. A higher information gain means a better split. The split data function is responsible for dividing the dataset into two subsets based on a chosen feature and value. This process is repeated multiple times to build the tree. To find the best way to split the data, we create the findBestSplit function. It loops through all features and possible split points, selecting the one that provides the highest information gain. The buildTree function combines all the previous functions to recursively construct the decision tree. It stops splitting when the minimum sample size is reached, the maximum depth is exceeded, or all labels in a subset are the same. Once the tree is trained, the predict function is used to classify new data points. It follows the tree structure until it reaches a leaf node, returning the predicted class. Next, we implement the Random Forest class, which combines multiple decision trees. During training, we use bagging, which is bootstrap aggregating, to randomly sample data and features, ensuring that each tree learns slightly different patterns. Finally, the predictions from all decision trees are combined using majority voting, where the most frequently predicted class becomes the final result. This makes Random Forest more stable and accurate than a single decision tree. Let's begin with the first phase, importing libraries and preparing the data. In Python, we often use external libraries to simplify our work. In this case, we are using 3 key libraries. The first one is NumPy, which is a powerful library for numerical computing. It allows us to efficiently perform operations on arrays, which is essential for handling large data sets. The second library is collections, specifically the counter class, which helps us count occurrences of elements in an array. This will be useful later when we determine the most common class in a decision tree leaf node. The third library is scikit-learn's function make classification, which allows us to generate sample data sets. This is mainly for demonstration purposes. In practice, you would use real-world data instead. Now that we have our libraries ready, let's move on to the next phase, which is building the decision tree class. A decision tree is the fundamental building block of a random forest. Essentially, a decision tree is a series of logical decisions that split data into smaller groups. Each split is chosen to maximize the separation between different classes, which allows the tree to classify new data points accurately. Let's break down the decision tree class step by step. First, we have the constructor, also known as the initialization function. This function sets up 3 important attributes. The first is min_sample_split, which specifies the minimum number of samples required to split a node. If a node contains fewer samples than this number, it will not be split further. The second attribute is max_depth, which limits how deep the tree can grow. If this is set to none, the tree will continue growing until no further splits are possible. The third attribute is tree, which starts as an empty variable, but will later store the actual structure of the trained decision tree. Next, we define entropy, which is a key mathematical concept used to measure how mixed a dataset is. A dataset where all samples belong to the same class has zero entropy, meaning it is pure. A dataset where classes are evenly mixed has high entropy, meaning there is a lot of uncertainty. The entropy function works as follows. First, it counts how many times each class appears in the dataset. Then, it calculates the probability of each class occurring. Finally, it applies the entropy formula, which is the sum of probabilities multiplied by their logarithms. If entropy is high, the dataset is very mixed. If entropy is low, the dataset is more pure. Now that we can measure entropy, we can define information gain, which tells us how much uncertainty is reduced when we split the data. The information gain function first calculates the entropy before splitting. Then, it divides the dataset into two subsets based on a chosen feature and value. It calculates the weighted entropy of these two subsets and subtracts it from the original entropy. The higher the information gain, the better the split. Now let's look at how data is actually split. The split data function takes a feature index and a value and separates the data into two groups. One group consists of data points where the feature value is less than or equal to the split value. The other group consists of data points where the feature value is greater than the split value. This function is crucial because it determines how the tree will divide the dataset at each step. To determine the best split, we use the findBestSplit function. This function loops through every feature and every possible split value. It calculates the information gain for each option and selects the one that maximizes the gain. If no good split is found, the function returns none. Next, we have the buildTree function, which constructs the tree recu. It starts with the entire dataset and checks if we have reached a stopping condition. These conditions are 1. If the number of samples is smaller than mean samples split, 2. If the maximum depth has been reached, and 3. If all the labels in the dataset are the same. If any of these conditions are met, the function stops and assigns the most common class as the final label for that node. If no stopping condition is met, the function finds the best split, divides the data into two subsets, and calls itself recursively on each subset. This process continues until every leaf node meets one of the stopping conditions. Now let's move on to making predictions. The predict function takes a new data point and determines which class it belongs to by following the splits of the tree. It starts at the root node and moves left or right depending on the value of the chosen feature. This continues until it reaches a leaf node, at which point it assigns the class stored in that node. Now that we understand how the decision tree works, let's move on to the next phase, which is defining the random forest class. A random forest is simply a collection of decision trees working together. Instead of relying on a single tree, we train multiple trees on different subsets of the data and combine their results. This makes the model more robust and accurate. The random forest class starts by defining 4 key attributes. The first is n-estimators, which determines the number of trees in the forest. The second is min-sample split, which controls how trees split their nodes. The third is max depth, which limits the depth of each tree. The fourth is max features, which determines how many features each tree considers when making splits. This adds randomness to the model, making it more generalizable. The fit function is responsible for training the random forest. It starts by generating multiple random subsets of the training data using bagging, also known as bootstrap aggregating. This means that each tree is trained on a slightly different version of the dataset. Then, a random subset of features is selected for each tree to use when making splits. Each tree is then trained using the decision tree class we implemented earlier. The predict function works by asking each tree to make a prediction for each data point. Since each tree might give a different answer, the final prediction is made using majority voting. This means that the most common prediction among the trees is chosen as the final result. Now that we have defined our random forest, let's generate some sample data. Using Make Classification, we create a data set with 100 samples and 5 features. 3 of these features contain useful information, while 1 is redundant. Next, we train our random forest model by calling the fit function on our dataset. We specify that we want 50 trees and a maximum depth of 4. Once the model is trained, we can use it to make predictions. To check how well our model performs, we compare its predictions to the actual labels using the accuracy score function from Sklearn. Our model achieves 90% accuracy, meaning it correctly classified 90% of the data points. To summarize, we first implemented a decision tree, which forms the foundation of our random forest. Then, we built the random forest by combining multiple decision trees. We trained the model on sample data and evaluated its accuracy. By using multiple trees and random feature selection, the random forest reduces overfitting and improves performance compared to a single decision tree. That concludes our lesson on implementing a random forest from scratch. I hope you now have a clear understanding of how it works and why it is such a powerful machine learning technique. Thank you for watching.